On the left-hand side of the board right now, you see a football helmet, a Calgary Stampeders football helmet, who, by the way, just beat the Eskimos yesterday to go to 8-1, I think. 8-1. First in the West. On the right-hand side, you see a train moving down the tracks. Not moving very fast, mind you, but still a train moving down the tracks. What do these two things that you see on the board right now, the football helmet and the train, have in common? Calgary Stampeders, 8-1, first in the CFL, not just the West. The train going down the tracks. Think outside the box here. What do these things have in common? Yep. Well, the Calgary Stampeders in general, right now. And not even all the time, but right now. What do the Calgary Stampeders have in common with that train? They have momentum. They have momentum, right? What does momentum mean? Forget about a literal physics definition of momentum for a second. Let's look at a definition for momentum that works for both of these things. They both have momentum. The Stampeders and the train both have momentum. Why do they have momentum? What gives them momentum? What do we have an understanding of when we say the Stampeders and the train both have momentum? Yeah, perfect. It's exactly the answer that I wanted there. They're hard to stop. When you come up against a team that doesn't lose very often, they're hard to stop. Well, a train is pretty hard to stop as well. Now, one of them is more of a psychological momentum, right? We're talking about a football team. Okay? Everybody gets confident. They keep winning. It becomes self-fulfilling because they're so confident, but it's still psychological. This is more of a physical momentum. Okay? Psychologically, it's hard to stop these guys. Physically, it's hard to stop this train. Now, why is it physically hard to stop this train? What about this train makes it hard to stop? There's a couple of factors here. Who can give me one single factor that makes this train hard to stop? Dustin, give me one. It's heavy. It's got a lot of mass. Mass matters for momentum. The heavier something is, the harder it is to stop. A number of years ago, we have two sons. My wife and I have two sons right now. We had one son at this time a number of years ago. And I remember we went out and we had a babysitter. He had to stop at the bank and get some money to pay the babysitter. The bank was the Royal Bank, the bank where our school division is right now, our school board office is right now, down at the four-way lights there in the middle of town. I stopped there on the road that faced the train tracks. I ran into the bank, got the money, came out, got into the car. I went to drive across the tracks, but as I'm getting to the tracks, the lights come on. The lights for the train coming come on. I look down the tracks, oh, there's a train coming. Okay, I'm not gonna go across the tracks. I don't wanna wait for this long train. So I turn down the alleyway behind where the town office is now. I go to the hi-ho, because I've got to switch one of the $20 bills for a couple tens for the babysitter. And then I come around, when I come around, the train is stopped right on the crossing. So now I turn down the other way, go down the other alleyway, going eastbound behind where our school board office is now, behind where the Royal Bank was at that time. And I drive 300 meters down, and there's a van, a minivan, that was right behind me waiting for the train that got T-boned by the train and went 300 meters, 3 football fields, down the track attached to this train. Why did it go 300 meters? I don't know how fast the train was going, to be honest, but I do know that it's heavy. And because it was so heavy, it had a lot of momentum and it was difficult to stop. That's why it went 300 meters. That's why you're not supposed to try to beat a train, because they have a lot of momentum. They're hard to stop. What's the other factor? What's the other factor that affects the momentum of this train, besides how heavy it is? How could something be difficult to stop even if it's not heavy? I ride my bike. My bike isn't all that heavy. It's pretty light. But sometimes it's difficult to stop that bike. Why? Because it's moving fast, the velocity. So how hard it is to stop something, its momentum is dependent upon two things: mass and not speed, but velocity. We define momentum in fact, as the product of mass and velocity. But we think of it, we understand it. A conceptual understanding is how hard it is to stop something. But these two definitions really go together, right? Why is something hard to stop? Because it's heavy, because it's got a lot of velocity. We're going to compare momentum to inertia. This is a term that you've seen before in Physics 20, and you've heard before in lots of places. What's the difference between momentum and inertia? We think of them largely in the same light, but they're not quite the same thing. Momentum is, let's look at this. How hard it is to stop something. Inertia is what? Be careful. You're partly right. The tendency of an object is said to keep on moving. That could be right. How could you expand that, though? Good. So the tendency of an object to keep doing what it's doing. The tendency of an object to keep moving is fine, but the tendency of an object that's at rest to stay at rest. So we talk about momentum as how hard it is to stop something. Something that's moving has momentum. Something that's at rest has no momentum. If something has mass, it has inertia, whether it's moving or not. We talk about how hard it is to change the motion, not how hard it is to stop it, how hard it is to speed it up, or slow it down, or stop it, or start it, how hard it is to change the motion. We'll say how hard it is to change motion. And that could be speed up or slow down, or start or stop. So let's look at a couple pictures here now. There's the train that I showed you just a minute ago. Now I got a second picture of another train. The first train, call it train number 1, is moving down the tracks slowly, but still moving down the tracks. Train number 2 is in a station. They both have more or less the same mass. Tell me, which train or trains have momentum? Train number 1, train number 2. Tell me which one or ones have momentum. Let's start calling on some people here. Jordan. Train 1 has momentum. How come? Good. Does train 2 have momentum, Jordan? Because it's not moving, right? So it's heavy, just as heavy probably as the first one, but it doesn't have any momentum because it's not moving. What about inertia now? So this one has momentum. This one doesn't. By the way, my son the other day, my son is 3 years old. We pulled up in front of the dollar store the other day. Just reminded me of this. He sees this sign in front of the dollar store. What does that mean? No parking, right? He gets out of the van and says, Dad, there's no letters allowed in the dollar store. Like, what? What are you talking about? I look at the sign. There's no letters allowed in the dollar store. My wife said, well, did you tell him what it really meant? I'm like, no. I said, it's funny. I'm not going to correct him. It's funnier. No letters allowed. Anyways, no momentum. Okay? It's got momentum. Second one doesn't have any momentum. What about inertia? Does the first one have inertia? Nick, does the first one have inertia? Yes, it does. How come? No, not because it's still going in the path. But it does have inertia, so you're half right. Why does it have inertia? Yep. Because it will resist a change in motion. Not, it is going in the same path. It will resist a change in motion because it has because it has, what's the word I'm looking for here? It's a 4-letter word, mass, because it has mass. Okay? It's got momentum because it has velocity and mass. It's got inertia because it's got mass. What about this one? Does it have inertia? Then, yes. How come? Because it's got mass. So you can see that sometimes you could have both momentum and inertia. Sometimes you could have just inertia. Can you ever have, here's a good question for you. Can you ever have just inertia and no momentum? Could you ever have just inertia and no momentum? Tara? Could you ever have just inertia, no momentum? What do you have to have inertia? There's that ugly 4-letter word again. What is it? Mass. What do you have to have momentum? Mass and velocity. Can you ever have inertia but no momentum? If you don't have any, if you have mass, sorry, yes, you can. So I asked the question the wrong way. Can you ever have inertia but no momentum? Yes. Can you ever have momentum but no inertia? No, because in order to have momentum, you have to have mass. If you don't have any inertia, then you don't have any mass. Does that make sense? Less sense than it was supposed to because I messed it up. But momentum is a vector quantity, which means what? Yeah, it's got direction too, magnitude and direction. You've got this much momentum to the east, not just this much momentum. I mean, it's dependent upon two things, right? Mass and velocity, a vector and a scalar, so it's got to be a vector. And finally, the main equation that describes the momentum, you guys can give me this one, even though you've never seen it before. It's staring you in the face on this page right now, the equation for momentum. What is it? No, but you're close. You're half right. Mass times velocity. We defined it as the product of mass and velocity. Now, this is a little bit tricky. The symbol for momentum is a lowercase p with a half arrow over it. James, ask me why it's a lowercase p. Like, shouldn't momentum be like a capital M or something? Ask me why it's a lowercase p. I don't know. Just is. Momentum is a lowercase p. I have no idea why. That's just the symbol we give to momentum. Just remember that. As opposed to a capital P, which is what? Uppercase P is, yeah, power. Good. Hey, how about some units here now? Mass. What units do we usually use for mass? Somebody said it. What units do we usually use for velocity? I'm sorry? Yep, good. Meters per second. All right. Here's the tough question of the day. What units would we use for momentum? I'll give you a hint. There's no shortcut like there is for energy or for force. The units for momentum are kilograms times what? Somebody said it. Don't be afraid to say it out loud. Kilograms times meters per second. It's not a shortcut. It's just combine the units that are in your variables, M and V. We get kilograms meters per second. Here's an example that appears in your textbook that most of you probably don't have yet, but that you can download tonight. 9.1 on page 451. By the way, that'll be the first chapter that you're downloading, chapter 9. And then we'll go chapter 9 through 17, I believe it is. It says a 180 kilogram bumper car carrying a 70 kilogram driver has a constant velocity of 3 meters per second to the east. What's the momentum of the car driver system? I'm not too worried about this last part here. I just want to know the momentum of the car and driver system. In Physics 20, both myself and Mr. Coderre taught you to write down your givens. That's the first thing that you should do. It's not really the first thing that you should do. The first thing that you should do is read the question and understand the question. Okay, get perspective on the question. But then you should write down your givens. What I'm going to allow you to do this year, largely because a lot of the questions that you'll see will be multiple choice questions, I'm going to allow you to write down your givens in a bit of a shortcut way. If you want to, say, circle this and write down V beside it, I'm okay with that. If you want to write it down the old-fashioned way, I'm okay with that too. Sometimes we're doing multiple choice questions. It's just a little bit quicker and easier to do it this way, but whatever works for you. All right, that's a velocity. What about anything else here? What else do we have given to us in this question? Yep. Mass. What's the mass? Good. Not 180, not 70, but 250. And we're looking for the momentum, right? So easy question, right? If you catch that, the fact that the mass isn't 180 or 70, if you catch that the mass is 250, then it's an easy question. Momentum is m times v. We get 250 times 3.0. What do we end up getting there? 7.5 times 10 to the 2. Why did I round that to 2 digits? 180, 70, and 3.0. Final answer should have 2 digits, right? What are the units here? 7.5 times 10 to the 2. Kilograms meters per second. Do we have a direction here? Jake? Yeah. If the velocity is to the east, so is the momentum. Done. Wow. People say physics 30 is so hard. Physics 30 is easy so far, isn't it? We're like 1% done physics 30 right now. And it's easy. It's still easy, even after 1%. It's still easy. Might get a tiny bit harder. All right, let's have a look at 2 practice problems on page 451. In both cases, or sorry, in the first case, we're asked to draw a momentum vector for the situation. I don't really care about that. Okay, the point of today's lesson is not to draw the diagrams. The point of today's lesson is to calculate your momentum. So do question 1A, please, and do question B. I'll give you a few minutes to do that. We'll take a look at them as a class here in a few minutes if we have to when you're finished, okay?